Thank you, and good evening, everybody. Yes, this is the first in a series about exploring the solar system, and this particular talk for the next half hour or so will be about how we explore the solar system using spacecraft. So I'll be saying a little bit about how we get there, how we actually get spacecraft to other planets. What do we do when we get there? How do we get images back? We go to other planets to explore them and find out about them. We want to make lots of measurements, but most people are interested in what do they look like close up? In other words, how do we get images if we send spacecraft out into the solar system? And then I'll finish by just asking what's next. Most of this is historical, but I'll also be saying something about missions that are coming up in the not so distant future. So when it comes to exploring the solar system, I started counting up, well, how many spacecraft have we actually sent from Earth that to some extent have either been looking at the moon or the planets or asteroids or other aspects of the solar system. I started counting them up and then realized I didn't have enough fingers. So I then started listing them, and I know you can't actually read this, but there's the list of all the spacecraft we've sent out into the solar system. Hundreds of them, hundreds of spacecraft have been sent up over the last 5 or 6 or 7 decades or so. I'm not going to be describing all of them because there's far too much going on there. But let me just give you an indication of how it is, for instance, we get to one of our closest neighbours, Mars. If that's the Sun and that's the orbit of Earth around the Sun, then Mars is the next planet out. I invite you to take a closer look at the orrery, the solar system there on the side, in the break between these two talks. But outside the orbit of the Earth, there's the orbit of Mars. So how do we get from Earth to Mars? Well, you might think that you wait until Mars and Earth are as close as they ever get, and then you go hell for leather in your rocket from Earth to Mars. Actually, in order to get from Earth to Mars, you actually arrange it so that you leave Earth at one point and you don't arrive at Mars until it's on the other side of the solar system. In other words, you follow that blue line as indicated by the arrows there. It might seem a little bit odd that you actually wait until Earth and Mars are as far apart as possible in order to get from Earth to Mars, but it turns out that's the most convenient way. It uses the least fuel. It's not necessarily the fastest, but it does use the least fuel. And most of the time, you want to minimize how big a rocket you need, how much fuel you need to expend, because the less fuel you use, the more scientific instruments or cameras or other things you can take with you. So that's how we actually get from Earth to our nearest neighbor. It's a somewhat egg-shaped orbit, an elliptical orbit that takes you from Earth to Mars. But Mars is one of the closest planets. What do we do if we want to go to some of the more distant planets in the solar system? Well, quite a long time ago, it was realized that we could use a slingshot, a bit like the Wile E. Coyote version, but not quite the same. Here, we actually leave Earth, and as we go past a big planet like Jupiter, we can slingshot. We actually use some of Jupiter's gravity to send us beyond Jupiter, in this case, to the next planet out, Saturn. This is what we did back in the 1970s. We sent probes, Pioneer probes, Voyager probes, went to the outer solar system, and they managed to get there in a reasonable length of time. It still takes years, but we can take quite a few years off the journey. Let me just run that particular animation one more time again. We can actually leave Earth, as indicated here. We go flying off towards Jupiter, but as we go past Jupiter, we use its gravity to slingshot us faster. Notice a dog leg there? It sends us off in a different direction and it makes us go faster, which means we get to Saturn even sooner. That's how we've explored a lot of the outer solar system. Jupiter, Saturn, Uranus, Neptune. All of these planets have been visited, and we use this idea of these assists, these slingshots, to get us there faster. And this was done in the case of Voyager 2, when it used multiple slingshots. It was launched from Earth, it used a slingshot from Jupiter onto Saturn, and then again another so-called gravity assist from Saturn onto Uranus and then onto Neptune. And since then, we've sent other probes even further beyond Neptune. This is one of the first images we ever got back from a body other than the Earth itself. It's a rather grainy, rather noisy image. Anybody care to take a guess what it is we're looking at here? What would you think it is? Sorry? The moon, very good. Most people would say, oh, that's probably Mars or Venus or something. But no, that's the moon, because it was taken by a spacecraft called Luna 3. And it was taken in 1959, before the days of digital photography. These days, we're so used to the idea that if you want to take a picture, you just click and you've got a picture. Back in the 1950s, that wasn't a possibility. So how did we get an image of the far side of the moon? Remember, the moon always faces, the near side is always the same, it's the one we always see. The far side is never visible from Earth, so we need a spacecraft to photograph the far side of the moon. How was this image obtained if we didn't have digital cameras? Here I've taken a little bit of the noise out just so you can see it's not a very detailed image, but it is actually quite accurate. But how we actually obtained that image is quite amazing, because for those of you in the audience who remember, what did we used to do before we had digital cameras? We used to have film. Remember those days? Emulsion, film that had to be developed. Well, that's what they did with this spacecraft. They took images on film, and then the film was put into a little chemistry lab, and it was developed and fixed and dried. And then it was scanned by a little sort of a flying spot that produced an intensity that told us how dense or not dense a particular part of the image was. And that information was then transmitted back to Earth, and that was used to reconstruct an image, a bit like a now defunct technology which we call the fax machine, where you send digital information, or at least information, over a phone line, and then it reconstructs an image at the other end. So that's how the image was actually taken. If we compare that with what we could do some decades later, some 50 years later, this image was taken a lot closer to the far side of the moon with digital technology, and we see that, well, okay, the resolution is now much better with digital cameras, but notice how, well, back in the 1950s, they got it pretty much right. Not particularly high resolution, but even with 1950s technology, you can still produce something useful. But ultimately, people from, for instance, NASA and other space agencies realized if we want to go to other planets and get images back, we can't just keep taking film and developing it and scanning it and taking the information back. We need something different. And so back in the 1960s, the Mariner spacecrafts were built, and they had, tucked at the very bottom of the spacecraft, the world's first digital camera. Not the world's first digital camera to go into space, the world's first digital cameras. That's why we've got digital cameras in our phones, because they were first built for spacecraft in order to photograph distant planets. And ultimately, the technology has now matured to the point where everybody's got one in their pocket. As this spacecraft was flying past Mars, it was photographing the Martian surface, and all the information that the digital camera was taken was stored onto magnetic tape. Again, for those of us who remember magnetic tape. And then, once it had flown past Mars, the tape was replayed and the information broadcast back to Earth, who could then, the people in mission control, could piece together the images of the Martian surface. Again, a little bit noisy, we can tidy it up slightly, but again, we can see surface features on Mars, craters, etc., with digital technology. We've now explored essentially every planet and some dwarf planets in the solar system, so we've sent probes out essentially everywhere in the solar system. We haven't visited every chunk of rock, but we have visited all of the big planets. We've visited a few dwarf planets, and we've visited quite a few moons as well. I haven't got time to tell you about all of those missions, so let me just pick out a couple to tell you about. Let's pick out the Cassini mission. This went to Saturn, excuse me, quite a few years ago now. It started its mission around 2004. And then it was deliberately crashed into Saturn in 2017 at the end of its mission. Why did they crash it into Saturn? Why didn't they just leave it orbiting, taking pictures for as long as it possibly could? Well, eventually it ran out of power, but the reason for crashing it into Saturn at the end of its life was because there is the outside chance, we don't know for sure, but there's the outside chance that some of the moons of Saturn might contain the right conditions for life to exist. And what they did not want to do is leave an Earth spacecraft orbiting such that in centuries to come it might accidentally crash into one of those moons and perhaps contaminate the moon. Therefore, it was deliberately crashed into Saturn. As far as we know, no life on Saturn. It's a big gas giant, even though there might be life on some of its moons. So you can't read all of the data here, but there are handouts. If you're interested in the numbers, you can take a handout away with you at the end. There were millions of commands executed. The spacecraft was sent out to Saturn. It took a long time to get there. It's traveled billions of kilometers or billions of miles. Millions of commands were executed. Huge amounts of data were sent back, not just images, but measurements of temperature of the planet and magnetic field and all sorts of other scientific measurements. Just to give you an idea of scale, that's the size of the Cassini spacecraft, and there's a person standing next to them. So you can see these spacecraft aren't particularly small. They're maybe half the size of this room, for instance. From Earth, we can see planets with this sort of detail. This is not strictly from Earth, this is from low Earth orbit. This is the Hubble Space Telescope, just a few hundred kilometers above our head, basically. And that's the sort of view of Saturn we get from the distance from the Earth to this particular planet. But if we send a spacecraft to Saturn, then we can see much, much more detail. For instance, the rings of Saturn, we can't see a huge amount of detail, other than we can see that the rings come in various shades of grey. But if we get close to Saturn, then we can see an enormous amount of detail. And we see the rings are not just a few rings, there are hundreds, thousands, tens of thousands, perhaps even millions of individual rings. Each ring is a whole set of particles, a whole load of tiny, icy particles all orbiting around Saturn. And it looks like there might be a very thin one right on the outside there. It's looking more and more like a long-playing record, again, for those of us who remember long-playing records. The more we look, the more detail we see. And the ring system itself, although it's made up of perhaps billions, more likely trillions of tiny particles all going round Saturn, it's a very thin system. The ring system is some 250,000 kilometers in diameter, much bigger than the size of the Earth. But the thickness of the ring system, it's one of the flattest systems in the solar system. The rings themselves might only be a few meters or perhaps tens of meters thick, even though their diameter is 250,000 kilometers. When the sun's at the right angle, it was actually casting shadows, and it was clear that part of the ring system is flat, but part of the ring system appears a bit lumpy. This region, you can see, I hope, casting shadows. Because the sun is in the direction of the yellow arrows there, these appear to be bumps because they're casting shadows on the rest of the ring system. So the ring system isn't perfectly flat, it's mainly flat, but some of it appears bumpy. And images like this are studied by scientists to try and understand why the Saturnian ring system has the structure that it does. And one perspective we can't get from Earth is, what does Saturn look like if it's lit from behind? We can never get that from Earth because we are close to the sun and Saturn's a long way away, so we can only see Saturn when it's sunlit. But a spacecraft can fly into the shadow of Saturn, and it can look at Saturn when it's lit from behind. So the sun is coming through the rings from the other side and also coming through the atmosphere as well. That gives us more information, because when scientists look at how sunlight is scattered when the sun is behind the ring system, it gives us information about how large the individual icy particles are that make up the ring system. So those sorts of observations are very valuable to scientists. Sitting on the side of Cassini was another spacecraft which was detached soon after it got there, and it flew into Titan. Titan is one of the moons of Saturn, and it's very interesting because it's not a huge moon, it's similar in size to our moon, but it has an atmosphere, whereas our moon apparently is completely arid and sterile. There's nothing going on there, there's no life, there's no atmosphere. But Titan appears to have an atmosphere, and so it was worth sending a probe in. So this particular probe, called Huygens, was detached from Cassini and was then parachuted into the atmosphere of Titan. And as it came down, it took this video. And now we know that the moon Titan, which has got a very foggy atmosphere, very difficult to see what the surface is like. When Huygens was sent into the atmosphere, we now know what the surface of Titan looks like. It appears to have mountains and rivers and lakes and clouds and rain, pretty much like Manchester. But this would not be water because this is so far from the sun, this is very cold, but it'll be made up of other elements, perhaps other compounds like methane or ammonia, perhaps methane. But it is a world in its own right. It might only be a moon of another planet, but it is a world with geography and with dynamics and with weather, and it is well worth studying. Another mission that's worthy of note is a relatively recent one called Juno, which visited Jupiter. This arrived in 2016. It's basically still going. Again, I'm not going to go through all the numbers. Many millions of commands were sent to this probe to tell it to point this way, take a picture of this, take a video of that, look at the moons of Jupiter as well as the surface of Jupiter. Jupiter itself, if we take it and unwrap it to get an idea of what the whole planet looks like, Jupiter has interesting weather systems. It has these winds that seem to be going east to west and west to east. And they are very strong winds, and we don't understand why various storm systems which exist in the atmosphere of Jupiter, we don't understand how those storm systems have persisted for so long. So we have strong winds, we have jet streams, etc. here on Earth, and we have weather, as we know from Storm Floris, for instance. But generally speaking, storms might last for a few days and then they peter out. But there are some storms on Jupiter which appear to have been ranging for hundreds of years. Galileo and other astronomers have seen storms on Jupiter hundreds of years ago, and they still seem to be there. So we don't fully understand how weather systems on other planets behave, which is why we're studying these, so we get a better idea of the dynamics of how this atmosphere behaves. The different colors almost certainly are from different compounds in the atmosphere, probably ammonia, probably methane, probably other elements, perhaps some phosphorus is in there, and each element gives rise to a particular characteristic color. So by taking images and other measurements, we can get a better idea of how Jupiter is behaving. But Juno gave us a perspective that we couldn't possibly get from Earth. Here it's going past one of the poles. Notice that as it goes past the pole, this is a time lapse. It takes a few hours to do a pass. Notice some white flashes occasionally. That's lightning in the storms of the cloud tops of Jupiter. But notice how structured the storm systems are, the structure of the atmosphere. We're now racing past the equator of Jupiter, heading off towards the other pole, and the spacecraft is now looking back as it recedes away from Jupiter. It's in an orbit which takes it close and then far away, and then close and then far away. And so it's doing lots of these swoops, getting closer to Jupiter, and as it does so, it gets these sorts of images, or in this particular case, here's a snapshot taken from that video. Again, we see the colors here have been enhanced a little bit to make them more clear. Most of Jupiter is this sort of salmony red color, but around the poles, it appears to be a lot bluer. And again, we're trying to understand what is the elemental makeup, what compounds exist in the atmosphere of Jupiter that give rise to these colors, and why do we get this peculiar structure around the poles of Jupiter. Here, this is again just a snapshot looking down as Juno passed only tens of thousands of kilometers above the top of the atmosphere. It's almost as if you're not looking at the cloud systems of another planet. It looks like you're looking at a watercolor or something like that. We think that black patch in the middle is a very deep vortex. It's very difficult to tell, but it might well be that we're looking into the cloud tops and we're seeing deeper into the parts of Jupiter which are not sunlit. But again, we really don't have all the answers to what it is we're seeing here. We should remember that the Sun, the solar system, is not simply the Sun and its 8 planets and the various dwarf planets and others. New Horizons, for instance, is exploring beyond Pluto. It went past Pluto, a dwarf planet, a very interesting system in its own right, and is now going beyond Pluto. And beyond Pluto, there's a large belt of icy objects called the Kuiper Belt, and New Horizons spacecraft is exploring one or two objects out there. It can't explore many of them because although there's a large number of bodies, space is really big, and therefore all of these bodies are separated by huge distances. But as well as planets and dwarf planets, there are also over 300 moons in the solar system, some of which are extremely interesting. Here's a collection of some of them. Some of them are recognizable as our familiar moon, always showing the same face towards us. There's the rather hazy looking Titan, where we can't see the surface because the atmosphere is so thick, which is why we dropped the Huygens spacecraft into that particular moon. Other moons, like this one, appear to look more like the Death Star than they do a moon, but that's just because it's being clouted with a very large object impacting, producing this particular crater. And some of the smaller ones look more potato-shaped. The large ones tend to be more spherical. The small ones can be very irregular shapes. And here's some of the larger moons in the solar system, the so-called major moons. There again is Titan, you can see, rather bigger than our moon, and again rather hazy, can't see what's going on. But there's a lot of interest in these four moons at the top there. Those are the moons of Jupiter: Io, Europa, Callista, and Ganymede. Io looks more like a pizza. That's because it's a volcanic planet. It's very close to Jupiter. It's always getting stretched and squeezed, and it has lots of volcanoes. But there's an awful lot of interest in the next three, Europa, Callista, and Ganymede, simply because they are ice moons, and you may think that's boring, apart from something like the planet Hoth. Apart from being an ice moon, why is that interesting? Well, it's not what's going on the surface that's interesting. We think all of those are covered in ice, but we have good reason to believe that below the ice, there's an ocean. Each of those probably has quite a deep ocean. And when I say deep, it's thought that the total amount of water on those three moons is greater than all of the water in all of Earth's oceans. So if you think of the Pacific and the Atlantic, these have got more water, but it's underneath ice. And to some extent, the ice is protecting it. The question is, if there's if there's water underneath the ice, if there's liquid water, and we do believe that that's the case, if there are various compounds present, and we believe there are various compounds, not just hydrogen and oxygen making up the water, there's lots of heavier elements in there as well, and there's some sort of heat source, well, there must be a heat source, otherwise the whole thing would be ice. To keep something liquid, like water, at this distance from the Earth, this distance from the sun, there must be a heat source. If you have an energy source, if you have the right elements and you have liquid water, you have the right conditions for life. There's no guarantee that there's life on the moons of Jupiter or the moons of Saturn, but all the right conditions seem to be present, which is why there's a great deal of interest in exploring these moons to find out whether or not there's any sign of life having started elsewhere in the solar system. And that's why there's two missions on the way. An ESA, a European mission called JUICE, Jupiter's Icy Moons, and a NASA mission called Europa Clipper. They're both on their way to explore more and find out more about the ice moons of Jupiter, because we think they are particularly interesting as places to look for life. We're also looking for life on Mars, but here we're also looking for life on the moons of the outer solar system. How do we get information back from these very distant places, regardless of whether it's just Mars, our immediate neighbour, or whether it's the outer solar system like Jupiter or Saturn or Pluto? Well, up till now, virtually all the communication with spacecraft has been by radio. The spacecraft have a big radio dish, and they send the radio signals back to Earth, and they are picked up by an even bigger radio dish on Earth. So you need a huge radio dish simply because the spacecraft is so far away, even if it's sending its information back to Earth, that huge distance means the signal will be very weak by the time it arrives on Earth. So you need a big dish to pick up the radio signal. But fairly recently, one development has been We've been using radio for, well, best part of 70 or so years. Why don't we use lasers instead? Why not use light rather than radio? They travel at the same speed. They travel at the speed of light. Radio travels at the speed of light, so it doesn't get the information back any quicker, but you can send more information in any given second by using a laser beam than you can by using radio. Those of you with fiber broadband know that you can get an awful lot of information per second down your fiber broadband by sending lasers. So the idea is it possible to put a laser on a spacecraft, and instead of sending a radio signal, you send a laser beam back and you pick it up with a big telescope, a telescope that's designed to look at light, to look at the light of the planets or the light of the stars. You use that telescope to pick up the laser beam sent by this remote spacecraft. So one that was sent up last year, they said, let's do a test. Let's see if it's actually possible. Let's send a spacecraft. Let's have the standard radio communication. But as a test, let's ask it to send something back via a laser beam. What are they going to do as a test? There's no point in just sending an image. An image is tiny. They wanted a proper test, lots and lots and lots of data. So they decided to send a video, a high-definition video from the other side of the solar system. What video are you going to send? Well, they said, we're sending information on a laser beam. So let's send a video of a cat chasing a laser beam. So they actually had a high-definition video of one of the NASA employees' cat chasing a laser beam. And they found that if the spacecraft was at a distance of 50 million kilometers away, they could get data rates of 260 megabits per second. That's faster than some people can get on their broadband when the information is coming from 10 miles away. But this is coming from 50 million kilometers away. And even when the spacecraft was much further away in the asteroid belt, 400 million kilometers away, they were still getting data rates of 8 megabits per second, much faster than they could possibly get by standard radio communications. So perhaps that's an indication of what's going to happen in the future. For the time being, we'll still be using radio, I'm sure, but it won't be too long before lasers will become the way that we communicate with spacecraft at enormous distances in the solar system. So if I've piqued your interest and you want to know more about missions that are currently going on, for instance, Bepi Colombo is a mission that's being sent to Mercury, and it's going to be in orbit around Mercury fairly soon. I can't remember if it's this year or next year it's going into orbit. Cassini has now plunged into Saturn, so that's now history, as it were. Juno is still going. New Horizons is still on its way out of the solar system. And as I've just said, we've got missions going to the icy moons of Jupiter, indicated down here. Don't worry about making a mental note of any of these web addresses. If you're interested, they're in a handout so that you can, if you wish, go and find out more about missions of spacecraft going to the solar system or missions in the near future that will be exploring various aspects of our solar system. Thank you very much.